So to review, when you are standing upright, your ventilation and perfusion are lower in the upper lung apex than the lower lung bases. So when you look at the top of the lungs, you'll see that the alveoli are larger. They receive limited blood flow, whereas in the base, the alveoli are smaller, but they get a lot of blood flow. They allow for greater expansion of the capillaries and thus more blood flow and oxygen exchange. At the top of the lungs, there is as much as 2.5 times the ideal value, causing um, a moderate degree of physiologic dead space. And remember what we said, the dead space are that area, so the lungs that do not participate in gas exchange. But when you look down in the bases of the lungs, in that picture there, there's about 0.6 times the ideal value, representing lower volumes of air where the blood flow exceeds ventilation. During exercise, your blood flow to the upper lung region increases dramatically, so it decreases that physiologic dead space. But with bed rest, the dependent area of the lungs becomes the back region, and in that laying position, so that blood flow is increased to that region, and the alveoli are smaller. So the alveoli are smaller in the dependent areas. There are different barriers that affects the diffusion and transport of gases at the alveolar capillary membrane. So as you can see there, oxygen and carbon dioxide have to go through red blood cells, plasma, capillary membranes, interstitial fluid, alveolar membrane, and then also have to go through surfactants. So if there's any abnormalities in any of those elements, then the oxygen exchange is impaired. So under abnormal conditions, such as diseases like pneumonia, pulmonary edema, interstitial lung diseases, that diffusion capacity of the lung tissue is impaired. There are two forms that oxygen is transported. It's either dissolved in the plasma, which is not very much, maybe zero point 0.3 mLs of O2 per 100 mLs are dissolved in the plasma. The rest of it is bound to hemoglobin. So oxygen binds to that iron in each of the four heme that's on the hemoglobin. And then at the tissue level, where the partial pressure of oxygen is low, oxygen is released from the hemoglobin molecule. So depending on what the tissue needs, 25% of the oxygen is normally unloaded at the tissues in a resting individual, which results in a venous blood being about 75% saturated with oxygen. When hemoglobin, though, is fully bound to O2, it is nearly 100% saturated. So what you'll see is a PaO2 of 95 to 100 mLs of mercury, increasing alveolar O2 concentrations to greater than what is needed. Then it doesn't really. So, for instance, what that means is that when your hemoglobin is already saturated with oxygen, by giving more oxygen to the patient, it's not going to, there's no place for the oxygen to get bound into the hemoglobin because there's no other places. It only has that 4 heme group. So in the lungs, where you have a high partial pressure of oxygen, the oxygen binds with the hemoglobin molecule. And in the tissues where partial pressure of O2 is lower, the O2 is released from the hemoglobin molecule, which makes sense because you want the molecule to pick up oxygen from the lungs, and then you want it to deliver to the tissues. So let's take a look at the different terms here. SpO2 is the oxygen saturation that's measured by your pulse oximetry. That's what you do. You put the thing on the patient's finger, it lights up. Essentially, what I tell the patient is this thing is measuring how much oxygen is floating around in your blood. It's what you're measuring with a pulse oximeter. So it's called an SpO2. Then there's the SaO2. This is the oxygen saturation that is measured by blood analysis. We kind of use this interchangeably when they say the SaO2, but really when you're measuring it with a pulse oximeter, it's the SpO2. When we say SaO2, that's the one that's measured by blood analysis. PaO2, that's the pressure of oxygen that is dissolved in the blood, and your normal range there is 80 to 100%.